Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about electronic schematics. So let's dive deep into it. So why do we need schematics? Well, the reality is that our electronics are getting ludicrously complex. I mean, like, damn. Like this sort of PCBs, yeah, these are the baby steps. Like you really do not even want to see what is the PCB design of a basically GPU used for computation, artificial intelligence. It's bonkersly difficult. And nowadays, the core motivation behind it is that IC development has like skyrocketed, meaning you can literally have a small black chip that can do so many things. Like we could have done the same things in 1990s. Only difference would have been it would be this big. Like you will have one section that's solely dedicated just to reading the temperature, one solely to store data, one just to do what it's supposed to do, one other have a feedback loop. And now we are like, black chip, sir. Take it and go, sir. Don't worry about it. And in terms of early days of computers, you should look into what was the chip pin count of Intel's first successful CPU. It was easy. You can count it. Nowadays, we start from tens of pins on a IC. We can go to hundreds to, like, for example, if you are dealing with CPUs or GPUs, CPUs can go up to 4,000 pin. And by the way, that's not the highest. There are some FPGA units that are like, let's not talk about it. That's how stupidly high pin counts we have to deal with. So it has reached a bonkers level, and many functions can be done by one. And now we're putting a lot of those units into one unit. For example, your motherboard could have a south bridge and north bridge, power factor correction, USB handshake devices, all of that. That's just on the motherboard without the CPU. So it's very difficult. What does this mean? It simply means at this point in time, you can randomly take an individual out of the street, like take just one random dude, does not matter which country, which continent, just take one out. Most of them will have no idea about how this world works. This literally looks like black magic to majority of humanity. And be mindful, it is actually black, so it actually looks like black magic. So this is why we need schematics. So you must understand this, like a human built this. It's not been imported from Mars or some Jupiter or Venusian individual built it for you. It's done by humans. So how does human do it? Well, we start with schematics. This is our first foundation. Many times people directly think into PCB. It's like PCB is the next stage. What's the first stage? First stage is schematics. So you come up with the idea. It's like, I want to do this. Let's say Anupam Vipul wants to do some. So for example, I want to basically build a fan controller, that ATX fan controller that utilizes pulse width modulation, and I want to read the RPM of it. Okay, so I have this idea. I have brings out the whole idea. So same way, this is a very simplified design. You may have something more complex. So you have an idea that will supposed to become the next magic box. So we built a schematics for that. And here's the deal. That schematics is also important after you have built it. For example, how the heck Louis Rossmann repairs Apple laptops? Well, he figures out how to get this. If he does not get the schematics, it's nigh impossible to do so. So repairing also becomes important. On top of that, there is also upgrading, version iterations and all that. So this document is important. This is not just lol. This is an important document. And again, it's a very easy way to find out a professional from amateurs. Amateurs generally do not pay attention to these stages, and professionals would be very methodic with this. Because be mindful, there is always a penalty of single human. If you are doing everything, there is a very good chance you're going to mess something up, which would be super obvious if somebody else just had a glance by with it. But if all your stages are messy, you're just getting through the output, you would have rushed it, you would have a sloppy documentation, and nobody will be able to help you properly. So it's very important as a basically repairing documentation, very critical. Back in the 90s, before the Anti-Repair Act, you could have literally called up a company and the company would have given you documents like this. And heck, many of the old machines literally had schematics bolted onto them physically. So it's a very important document. Again, very important for repair and very important to actually build the damn thing. Now, what's the intent behind it? What you're supposed to get out of this? Well, they're supposed to be easy to read and understand. Meaning, I look into this, I'm like, I got you, fam. I'm like, okay, what is this? This is basically this development module of Vroom 32E. Vroom 32E module. I want to read it. Okay, cool. What is this? This is USB-C. What is this? This is this USB to serial converter. What is this? LEDs. What is this? RGB LEDs. What is this? This is the power relay controller. Not power relay. Yeah, this is the basically 5 volt to 3 volt output. What is this? This is the latching mechanism. What is this? This is the boot button. This is the reset. That's the intent behind it. Basically, whatever is here, I can look into this and I'll be like, okay, I got you what's happening. And this is the controller. So That's the intent behind it. It's supposed to be a document that is easy to read, easy to understand. Now, could this have been made even better? Absolutely. It's one of those things, like you should spend time. And if you're really doing it for, let's say, a very professional reason, open source reason, or you want, like some people are very methodic with this, they go all in, and you can look into it. It looks like an artwork. It's like, follow the line and you're like, I got this. So it's very easy to read. That's the whole point of this documentation. Easy to read and understand. And this tells you what's happening and how it's happening. For example, it's like, okay, this IC is communicating with PC. How the heck that's happening? I look at the schematics. First thing I'll find, okay, there are pins. Okay, good, awesome. Pins are talking to what? Pins are talking to the module. Okay, awesome. How the heck module is talking to something else? Okay, I will look into this and I'm like, okay, this is the chip CH343P. And this puppy is communicating with D plus and D minus. D plus and D minus is going to this D plus and D minus. This is USB-C jack. That's how I can follow it. This is USB. This is the converter. This is the module. Modules have the outputs. That's the whole point. What is happening, how it's happening. This is what it means. Now, here's the, there is no standard format like dot schematics. There is no standard format for that. However, that being said, people generally prefer it to have vector characteristics into them. Meaning, if you want an easy to read schematics, generally, whatever application you have, most of the proper application will give you an option to save the file as vectors. Vector simply means you can zoom in as much as you want. It's mathematically described, not a pixel value. It's not a raster, it's a vector. So, for example, this is a good PDF. I got downloaded this here, awesome. But here's the deal. How do I look into this? Because there's a lot of high pin density. This is the zoom out of it. Like 500% you can easily zoom in. So generally people prefer PSD for this reason. And this is the easiest way to figure out either somebody was rushing out or somebody professional doing it. Professional will always use, the vectors. Because again, if you have complex designs like this, like FPGA units and all that jazz, whoa, like if you cannot zoom in, you simply won't be able to see it. If it's a like JPEG, yeah, God help you. JPEG, PNG, it's useless unless the file becomes bonkersly huge. So generally people always prefer vector for schematics. So it's the easiest format to carry it, even easier than direct scalable vector graphics, SVG. It's generally have PSD. Because portable documentation does have the vector engine built into it, so you can just carry it forward. Very easy to print also. So this is how we generally share this puppy. So how it's written now, if you are as in, like this was my first favorite movie, Iron Man 1, and this was like I blown away in the theater when I was just like, tweet. So I never understood what the heck he was doing. Now I can, okay, this is just a schematics board. So he basically mass producing schematics. And most of the symbols are hulululu, but it's like, I get it. I get the intent behind it. So this world of schematics has its own language. It has its own symbols. You have to understand that. Thankfully, it's very universal, meaning you can literally look at the schematics made in Japan, schematics made in Europe, schematics made in India, or whatever have you. It's not that difficult, thankfully, at least. This part we are kind of good at it. So it's very universal. Now, again, some minor differences could be there, some software to software could be differences there, but if you're paying a little bit of attention, it's minor inconvenience at best. It's super easy. Thankfully, a lot of symbols are very universal. Resistor, diodes, op-amps, inductors, transformers, things of that nature. It's like super easy. It's not that difficult, thankfully. And here's the complex part. Like these are the simple elements like a resistor, diodes, and all that. What about the modules? What about ICs? Thankfully, those are described quite easily. Tada! It's just a box. So, for example, ESP32 module. How the heck that module would be drawn in schematics? Is just a box that will have the name that this is a module, and it will have pin counts. Nothing more than that. You do not have to do more than that. So it's a very easy way to convey complexities. Like you can convey, like nobody's gonna draw a full, CPU processor. All they're gonna draw is like a, basically a square, and they will have as many pins needed. I really want to look into those people's file. It's like, yeah, 4,000 pin. Figure it out in a motherboard. It's like, damn. So same rule applies. You just have a box that has pins coming out of it. It's easy to learn. It's quite easy. And now here's the how the heck you connect it. Generally, lines are the connection. And how would you know whether lines are sorting it out or not, just passing it through? Well, here's the deal. It is made for human understanding. It's not an inherent documentation. So we figured out a simple way. It's super easy. If you can just crisscross lines, okay, then how would you show that line is actually connected? For example, this line, ground 2, it goes through all those pins. Like it goes through engage pin, 36 pin, 3 to 14 pins, it just goes through it. Does it sorting all of them? No, hell no, it's not even touching it. How do I know? Well, there is no dots there. So wherever you see like ground and you see dot, that means it's connecting. You see capacitor dot, it's connecting. That's how we figure it out. It's a language, almost universal language in almost all schematics. If line is crossing there and there is no giant circular dot there, that means it's not touching. If it has dots, it means it's an electrical connection. So that's just one annoying thing. But again, sometimes people do trace it out like a PCB where it's not touching anything. It's way too tedious. And PCBs have the advantage of 3 dimensions. This is a 2D documentation. That's why we prefer this route. So symbols are there, and this is like it took me way too long to understand what the hell this was, but now I do. So where the heck we get all this data from? Well, here's what's the source. Source is generally anytime you want to build anything nowadays specifically, most likely you're going to deal with IC. It could be a 4-pin IC to like a 36-pin IC or bonkers amount of it. So we generally start with that. Even if you are dealing with something very simple, let's say just power regulator or MOSFET, something, not even MOSFET, let's say linear regulator. You just want like 5 volt in, 3.3 volt out. You will find a data sheet for it. That's the first starting point. And this is the first thing you have to understand. You are dealing with electronics, get to the data sheet. That's the compulsory requirement. Like you get the data sheet, you can survive. Data sheet generally contains schematics for getting you started. For example, this is a USB-C breakout board. I plugged USB-C in, it gives me outputs. What are the outputs? You have V bus, which will be the positive rail. We have ground, which will be the ground. And we have CC1, that is requirement for USB-C. And CC2, requirement for USB-C. And data plus and data minus. Okay, cool and awesome. But here's the, can I get... sorry about that. Can I get a power delivery out of this? No, it does not have any data basically sensor where it's gonna actually talk. There is no handshake device here. So I can buy this puppy, CH224. Now if you have recently paid attention to Amazon, eBay, things of that nature, you may have paid attention to, there are a lot of devices like this which are called power delivery decoy boards. You connect them to USB-C charger and it gives you 9 volt, 12 volt, whatever have you. How the heck that's working? They are utilizing this IC. So this is a data sheet of this IC itself. So they are giving you a rough schematics. Same things. VCC, DP, DM, C plus, data positive, data negative, CC1, CC2 and ground. And this is how you're supposed to connect it. And they are giving you a very easy to read data. Where it's like, hey, you connect 6.8 kilo ohm resistor. We're going to assume that you want 9 volt output. We're going to handshake 9 volt. You put a 24 kilo ohm. We're going to assume you want 12 volt, we're going to do a handshake with that. You put 56 kilo ohms, we're going to assume you want 15 volt. You put nothing, not connected, we're going to assume you want 20 volt. You want maximum power delivery standards. Okay, go you learn it. Again, this same design will go into other manufacturers. Some boards are like, just fixed voltage. Other boards are configurable. You can configure it. So the configuration, they are giving a very easy example here where you have a checkup chart. And the chart base is like if it's 100, it's 5 volt. It's 000, 9 volt. 001, 12 volt. 011, it's 15 volt. 010, 20 volts. So that's how you get it. Like this is generally the starting point. Whatever you are saying, be it simple devices, be it bonkersly complicated device, that's how it starts. You will always look into the source data sheet, and these people who are building the damn device, they also put a lot of effort into actually making the schematics because that's how they test it. So once you have, like for example, this is another device, I may be building this MP1584. So this puppy is a buck converter where you can take in like a voltage, variable voltage, and get a very low voltage, lower than that output. And because it's a very high frequency device, it is very small, tiny devices. How do I know how to connect it? Do you think that electrical engineers just know? No, they don't know. They look into the data sheets like, okay, they can study it. They can study the language. They understand, oh, this means capacitor. Oh, this means diode. This means inductor. That's what it means. That's why schematics is so important. It's the language that allows manufacturers data sheet to talk to the electrical engineer, talk to the consumer is like, I want this. How the heck that data goes to the manufacturer? Through this. Schematics helps them bridge the gap basically. So schematics is always your getting started point. And this is how you start, and then you can build on top of it. You can go use different ICs. Sometimes ICs literally will be pin compatible, so you can literally replace one from the another. It is general for something that is too popular. That also allows you the advantage that, hey, supplier gets down for some reason. You're like, okay, I'm going to switch the supplier. That is a requirement. You must be competent in that. So this is the source of it. This is how everybody starts. Okay, so far I talked about what it is, how it is, and all that. How do you physically build it? Well, thankfully, there's a lot of FOSS option to paid options. FOSS option simply means free and open source software. So that's good. But there are also paid software, and you may like, why would anybody want to pay? Well, paid software generally have a good user interface, and there is somebody who's taking reliability, accountability for it. So that's why still we have paid software. So KiCad is a very good free and open source software that a lot of people are trusting, and it's good. It's good. It's working. It's effective for many people. That's a very good solution. Then we have Easy EDA. This is how I'm going to start with my electronics journey. This is also free and open source, and it's also web based. Easy EDA is a company that physically makes the PCB. So you can use this software and get the physical product built into you, built and mailed back to you very easily. And the primary reason why I'm focusing on Easy EDA rather than KiCad is simply because this has the best library, meaning all the symbols that I can just type the model numbers and get good reliable symbols. Not absolutely, there is no guarantee there. And Easy EDA have been working their ass off to filter out the library. Again, depending on your experience, some people are like, dude, I get awesome results out of that. Other people are, dude, half of the footprints are wrong and all that. That's up to you. But Easy EDA generally has a much better library. If you want to be very methodic, you can go with KiCad, because again, most of the time people may want to prefer to just build everything. And if you're working with something sensitive, some device that you would not want to be cloned, you may be like, hey, I'm not trusting the online security. How about I use KiCad? These are two free options just to getting started. For most people who's starting out, Easy EDA, good option would be there. Then what about professional people? Altium Designer is there. Then you have Cadence. Then you have Mentor. Now, how do we know that these are professional? Going to job searching site, these three pops up a lot. Like we are looking for 2 years experience in this, 4-year experience in this, and all that. So this is how we know these are the pro level for like Apple, Intel, things of that nature. Altium Designer, Cadence, Mentor, these sort of puppies. And there are many more. Let that be very clear. I'm just talking about the basic one. There are many more. So this is how we start. Now be mindful. I would urge you, if you're really even curious about electronics, go into this. You would be shocked how easy these tools have become compared to in 1990s. Like you can go in, dive deep into it, make your puppies, and you're just like, whoa. And be mindful, you were like, okay, let's say I made the schematics. What about after that? Most of these software have auto router, and unless you are building something very complex, you would be shocked. Auto routers are actually good nowadays. I'm just waiting for somebody to put a good AI into it, and it's like, done, bro. And yes, there are companies working their ass off to get this. And many of the complex board, humans don't even build it. They build AI to build it. And if the human's job is just to filter it out. So it's like taking data from design regulation rules, because again, PCB cannot be just made out of whatever you want. There are some rules and regulation on that, from law based, basically EMF creation based, and chemical etching process limitation, meaning you cannot just have like 90 degrees everywhere. It's not a good idea. So all of those goes into the design documentation, design limitation, and this software will sort all those things out. There are very advanced tools nowadays. Like you should not hold yourself back. Like if you're like, hey, I'm sloppy with this sort of thing, trust me, start with this and you'll be like, damn. You will be surprised by yourself. I guarantee it. So this was my presentation on schematics. What it is, what's the deal behind it. Hopefully you guys have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.